Hey, so it's nice to be giving this talk after Shan's nice talk, which also motivated the sublinear matching problem. So this talk is about recent advances in algorithms for sublinear time maximum matching. So I don't need to define the maximum matching anymore. We've had already 3 other talks on matchings. But like the red edges here form a matching because they're a set of vertex disjoint edges. Matchings have numerous applications. We love to study them, and they've been studied a lot. We've had fast algorithms, relatively fast algorithms, culminating in a combinatorial, roughly M-root 10-time algorithm in the 70s and 80s. And then there's been these set of breakthroughs based on continuous optimization methods, going all the way down to close to linear in the number of edges. Rasmus gave a very nice tutorial on how this is possible. And I just wanted to also mention, Cheyenne also mentioned this, that if you just want a 1 minus epsilon approximation, there's a very simple folklore linear time algorithm. But what we'll focus on today is, can we go below linear time? Can we design algorithms that run in time sublinear in the input size? One thing that we have to note is that when you talk about sublinear time algorithms, we do not even have time to read the whole input. So we can only read a very small fraction of the input. And because of this, it becomes super important how the input is represented. Two models are common for graph problems. The adjacency list model and the adjacency matrix model. Basically, we have query access to the graph. In the adjacency list model, for every vertex, we have a list of the IDs of its neighbors. We can query this list for every vertex. In return, we are given the IDs of those neighbors. In the adjacency matrix model, we have an n by n Boolean matrix. You can query if these 2 vertices are adjacent or not. What are the trivial bounds? In the adjacency list model, you can query everything. The total number of entries is the number of edges in the graph, or the number of edges in the graph, because every edge appears twice. And in the matrix model, it's n squared. Unfortunately, these trivial algorithms are optimal if you want to find any constant approximate maximum matching. And we will actually see why this is the case. It's not hard to see. However, let's focus on the more modest goal of just estimating the size of the maximum matching instead of returning the edge set of the matching. And for this problem, you can actually do non-trivial things, and the problem becomes super interesting. So today, I'll only focus on the adjacency list model. But pretty much many of the algorithms I mentioned also translate to the adjacency matrix model, just assuming that the matching is large enough. OK, so let's see some basic lower bounds. So let's start with multiplicative approximations. Suppose that we have adjacency list access to the graph, and we want to multiplicatively approximate the size of the matching. Now, here is a barrier. Suppose that the graph is either empty or there's just one edge somewhere in the graph. So it's the output is either 0 or 1. The size of the maximum matching is either 0 or 1. Distinguishing them requires finding whether there is this edge in the graph. So you have to scan the adjacency lists of the n vertices, requires omega n time. But this is not an interesting lower bound, because in many applications, you can assume that the matching is large. Shannon, for example, motivated why you can always assume that matching is at least linear in the number of vertices in the dynamic setting. Nonetheless, this lower bound of omega n also translates even if the matching is large. And here's the idea. This is due to Parnas and Run from 2007. So suppose that the graph is like this. So it's either drawn from the left distribution or from the right distribution. So here, we have, in both instances, we have some epsilon n vertices adjacent to every other vertex in the graph. The only role they're playing is just to increase the number of edges to n squared, while not changing the matching by much, because they can only change the matching by epsilon, and only these epsilon n vertices will be matched. Now, what becomes important is whether the rest of the vertices have a large matching among them or not. Now, on the left, there's actually a perfect matching among them. On the right, there's nothing. So here, the matching is large on the left. The matching on the right-hand side is small. To separate them, we have to find at least one of these edges for the size. And finding any one of these edges requires scanning the adjacency list of its endpoints. And they have epsilon n neighbors among these dummy vertices. So you're going to have to spend omega n time just to find one edge in the matching. And that's actually why for finding any constant approximation, you have to spend n squared time, because finding a constant fraction of these edges would require spending n time for each one of them, overall n squared time. Though I'm cheating here a little bit, because you can just query the degree of a vertex and tell apart these two distributions, but that's easy to fix. You can just add stars to the right-hand side. All the vertices we now have the same degrees, except those two vertices which are hard to find in less than n time. So this is a formal lower bound that omega n is needed, even if the matching is large. All right. So there's been a lot of exciting work on the algorithmic side. I call these classic algorithms. These are algorithms from around more than a decade ago. Most of these algorithms focused on, OK, my laser is not working. OK, yeah, so most of these algorithms considered graphs of low degree. So if the maximum degree delta is small, think of it as constant for now. So for example, Parnas and Ron showed that you can give a half approximation of the size of maximum matching in time delta to log delta, which is pretty fast if delta is small, much faster than reading the graph. So this delta dependency has improved over time. In an elegant work, Yoshida, Yamamoto, and Ito improved it to polynomial in delta. And there were further improvements. But note that all of these algorithms require at least n squared time when delta is unrestricted, when the graph can have degree as large as n. But there's been a second wave of results. The first one was due to Kapralov et al. In Sora 20, who showed that you can find a constant approximation of the size of matching in order n time. This constant is very large. Later on, Chen, Canon, and Kana improved it to half approximation, worsening the running time a little bit to n root n. This is the result that I'll talk about. You can improve you can get a half approximation also in n time, matching the Parnas-Ron lower bound of omega n for any constant approximation. And there's also been a lot of other improvements. For example, we showed that with Mohammad, Aviad, and Amin, we showed that you can beat half a little bit, spend a little bit more time. Then with same co-authors and also independently by Shayan, Peter, and Tachapal, this was improved to 2/3 in subquadratic time. And later on, in this very nice result, Shayan, Peter, and Tachapal improved the approximation to 1 minus epsilon while still keeping the running time subquadratic. So this is a lot. But if I just want to summarize and just state the state of the art, we have half approximations in n time. This is time optimal, matching the Parnas-Ron lower bound for any constant approximation. There's this other result that obtains a little bit better than half approximation. It's still close to n, but it's n to 1 plus epsilon. It's not n polylog n. And there's this third result, which is a 1 minus epsilon approximation in subquadratic time. All right. So what I want to do is I want to give you a brief overview of the first result, how we can actually estimate the size of the matching, knowing that it's hard to find the edge set of the matching. Okay. Any questions so far about the problem, the setting? All right. OK. So what's the general idea? This general framework is actually due to Parnas-Ron in the original 2007 paper. This is how they estimated the size of matching. So let M be some fixed matching in the graph. For example, think of it as we fix some matching, for example, randomized greedy maximal matching, which Shayan defined. We do not know the matching. We have not computed the matching. But it exists somewhere. If you fix, for example, the randomness, it's just some fixed matching. And now suppose that there's some oracle that if we're that if the oracle is given some vertex v, it returns if v is matched in this matching or not in some q time, or q queries. And now the framework works as follows. You sample some t vertices, run the oracle on these t vertices, see what fraction of them get matched, and use this to estimate what fraction of vertices in the whole graph are matched. So in particular, you take the number of sampled vertices that are matched divided by t. This is the fraction of vertices matched. You assume this is roughly approximates well the ratio in the whole graphs. So you multiply it by n. This gives you the number of vertices matched divided by 2 because you want to count the number of edges, not the vertices. Okay? So this is a very simple framework. And the overall running time of this framework is q times t. Q is the time needed by the oracle. T is the number of samples that we take. And for the rest of the talk, think of t as constant. If, for example, you assume that the matching is large enough, 1 over epsilon squared suffices for t to get an additive epsilon and error. If you want a multiplicative approximation, t will be a little bit larger, but for now, assume that t is constant. The real question really is, how much does the oracle need to spend? How much time does it need to spend to answer whether a random vertex is matched or not? All right. Yeah, and it depends on the choice of m. Like, what matching do you fix? You also have to define what the oracle is and then start analyzing how much it takes for a random vertex. Okay? So I'm going to talk about the half-approximate algorithm running in order n time. The matching m that we fix is going to be the randomized greedy maximal matching, which Cheyenne defined, but here I'm going to quickly define it again. So you have an ordering over the edges. You process the edges one by one in the order of this permutation, this random permutation. So for example, edge 1 joins the matching, 2 does not because it's already incident to 1, then 3 joins, then 5, then 7, 8 does not, 9, and then 11. Okay? Right, so as I said, we cannot find a constant fraction of the edges of this matching in subquadratic time. So instead, the oracle that we want to design should answer these queries more locally. And yeah, so this is a maximal matching, so it obtains a half approximation. It only remains to define the oracle. And the key intuition behind why this is possible, potentially, is that an edge E belongs to this matching, M, this greedy matching, M, if and only if no lower rank edge is incident to it that's also in the matching. So for example, edge 5 is in the matching because all the lower rank edges incident to 5, which would only be 4, is not in the matching. But on the other hand, 12, for example, is not because 9, which has a lower rank, is already in the matching. Right? So this is a simple observation. And it actually immediately translates to a recursive process for determining if a vertex is matched or not. How does it work? This was first suggested by Onak and Nguyen in their nice Fox 2008 paper. So suppose that we want to know if edge 11 is part of the matching or not. So you should first recursively query the lower rank edges incident to 11. So you have two choices. You can query edge 6 and edge 10. It actually makes more sense to start with 6 because it's more likely to be in the matching. It has a lower rank. And immediately after you find a matching edge, you can terminate the process, say 11 is not in the matching. Okay, so just finding one edge incident to it that's in the matching suffices to tell that this edge is not in the matching. So we, starting from 11, we start querying 6. 6 recursively queries 5. We go so on and so forth until reaching edge 1. 1 does not have a lower rank neighbor incident edge. So what we get is that 1 has to be in the matching. Okay, so there's nothing else preventing it from being in a matching. And then we backtrack. So 1 being in the matching implies that 2 is not in the matching. 2 not being in the matching implies that 3 is in the matching because 3 doesn't have any other edge. We backtrack all the way to 11. Now 11 sees that 6 is not in the matching. But it doesn't mean that 11 is in the matching because there's another lower rank edge that would be 10. So this continues, right? So this continues. And this would be the basically the subgraph that we explore to determine if edge 11 is part of the matching or not. Yeah, so we generally hope that this is a small subgraph of the graph running fast. However, as you can see in this example, at least, this is exploring pretty much the whole graph. However, if we started, for example, with another edge 12, 12 would first query 8. 8 would query 7. 8 is not in the matching. But immediately after 12 queries 9, we get that 9 is in the matching. And so we terminate the process. So the 12 does not query 11. And so that's why the explored subgraph of 12 is much smaller than 11. Okay? So now the question is, what happens for a typical edge or a vertex? Can we say that if you pick a random vertex and a random permutation, this is smaller than exploring the whole graph? So to make things a little bit more formal, define this quantity q, v, and pi to be the number of edges explored by the oracle to determine if a vertex v is matched in the greedy matching according to this permutation pi. So in the original paper, Onalk and Nguyen, who defined this oracle, showed that for any vertex in the graph, so long as this permutation is random, the running time is at most e to delta. And this basically bounds all the monotone, all the edges reachable from this vertex v via monotone paths along the ranks. Right? So if you reach a vertex, you better have gone through a path whose ranks are monotone. And this bound is actually tight for monotone paths. What this is not using is the fact that you prune if you find a matching. Right? So if you see a matching edge, you immediately prune. You do not see the rest of the incident edges of that edge. And that turns out to have a significant effect on the query complexity. So in their very nice result, Yoshida, Yamamoto, and Ito showed that for a random permutation, and now, unlike the result of Onalk and Nguyen, if the starting vertex is also random, which is the case in our application, remember we take t random vertices, then this quantity q is actually upper bounded by the average degree times max degree, so max degree squared, basically. So from an exponential dependence on delta, it immediately improves to polynomial, which is really nice. The problem is delta squared still can be as large as n squared. So basically, my result was a refinement over the analysis of Yoshida, Yamamoto, and Ito, combined it with some recent advances in parallel algorithms, and basically achieved an almost tight bound on up to logarithmic factors that this quantity qv for a random vertex and a random permutation is within the average degree and average degree times log n. Okay? And yeah, so it takes a little bit of work, but this quantity is actually really the running time of the sublinear algorithm. So this is how you get an order n time algorithm for half approximations. To wrap up the first part of the talk, yeah, so there are half approximations for sublinear time matching running in order n time. There's a 1 minus epsilon approximation running in subquadratic time. And there's a slightly better than half in close to n time, but not quite n. Any questions about the algorithm or the result?
So your starting vertex is random and your permutation is random. But in your query model, when you start with an edge, you start with the incident edges of the lowest rank. And you said that was sort of intuitively because lower rank edges are more likely to have been edges.
Exactly.
But doesn't that depend on the kind of the graph structure or something? Like, is there anything else that could have been exploited, such as some distribution on these edges or something like that?
Oh, I see. So you're asking if there's even a better oracle.
It seems to me that that's the part that's not random, right? That's the part where once you fixed your random permutation, you're starting.
Yeah.
Is it completely obvious why that's the most natural?
It's natural because you want to query edges, neighbors that are more likely to be in the matching, so you prune fast. So that's the only intuition. Maybe you can get some property of the graph and decide in another way. That would be super interesting. Yeah, I have no idea. Yeah, great question. Um, yeah.
Is the runtime of your algorithm proportional to maximum degree then? Or?
So yeah, that's a very good question. Yeah, so the bound was average degree times log n. So actually, if you want a multiplicative additive approximation, it runs in average degree time. If the number of samples is constant, it runs in average degree over epsilon squared time times some polylog n. But I'm writing on order n because it actually works. It actually gives a multiplicative approximation as well. For that, you're going to need a little bit more samples than constant. The samples are going to be in the order delta over average degree, so it's going to be actually delta. And there's a step when you have to throw out singleton vertices. So that takes n time. So overall, it's n, and n is necessary, actually, if you want multiplicative approximations. Yeah, great question. Yeah.
Is there any chance there's a deterministic version of this algorithm?
Yeah, I really want to say no, but I don't see how. If this can be made deterministic.
I think there are lower bounds.
Yeah, I think so. OK, yeah.
I was curious about the nature of the lower bound. It's like, so you showed for this particular set of queries you have a lower bound. Is there like a natural notion of query that would allow you to break through that, or are there lower bounds that show that even if you allow more complicated queries at a certain time?
So the Parnasson run lower bound that I mentioned says that if you want any constant approximation of the size, you better spend at least omega n time. Even if for any algorithm and any oracle, omega n is needed. So this actually just matches that bound. And I will see for the next part of the talk another better lower bound for this problem, if you want better approximations than just a constant. OK. All right, so basically now, as you see, the algorithms have been improving. And a very natural question here is, how far can we improve them? For example, is it possible to get all the way up to 1 minus epsilon approximation in just n polylog n time, matching the Parnasson run lower bound for basically any arbitrary good approximation? That would be a very nice result, because it actually would resolve the question that Shayan mentioned about maintaining a 1 minus epsilon approximation in polylog time in the dynamic setting. Unfortunately, we showed that this is not possible. So with Mohammad, Roghani, and Aviad Rubinstein, this past talk, we showed that for any fixed epsilon, for any fixed positive epsilon, if we want a better than 2/3 plus epsilon approximation, then the algorithm has to spend at least n to 1.2 time. So this is the first super linear in n lower bound, breaking the Parnasson run lower bound. And the only extra assumption is that we want a better approximation than just constant. This cannot be true for any constant, because as I showed, a half approximation can already be obtained in order n time. Yeah, so this is basically showing that there's some non-trivial trade-off happening between the approximation ratio and the running time of sublinear time matching. Okay. All right. So I'm going to give some rough intuition behind why this lower bound holds. So I'll start with a distribution that's wrong. Actually, it's not the final distribution that we proved the lower bound with, but it's still very insightful. So how does the distribution work? So we still have these dummy epsilon n vertices made adjacent to every other vertex in the graph. The only role they're playing is to increase the number of edges to n squared while not changing the matching much. Okay. So the main action is happening in this induced core graph. Okay. And what do we have here? So we have 6 sets of vertices, actually 3 maybe. So we have A vertices, B vertices, and S vertices. The S vertices are singletons when you look at the induced subgraph of the core. So they still have epsilon n edges to the dummy vertices, but they're singletons inside this core. There is a D regular graph from A vertices to B vertices. Yeah, this is not, OK. Yeah, so my pointer died. But there was this other one I can probably use. Yeah, so really this is, oops, OK. Yeah, so no pointers for me. OK, so from A vertices to B vertices, there's a D regular graph. And these, think of it in the order n to the 0.2. And we're at the end going to prove an ND lower bound. And the only difference between the A vertices and the B vertices is that the B vertices are adjacent to the singletons, whereas the A vertices are not. OK. Now, I'm going to give two distributions. One is a no distribution where the matching is small. And I'm going to give a yes distribution where the matching is large. And if you give a better than 2/3 approximation, you have to distinguish these two. So this is the no distribution. And the red edges here pretty much form almost a maximum matching. Why the singleton vertices S don't have any choice other than getting matched to B. So let's just match them to B. And the A vertices have no neighbors to get matched to. So in this example, in the no instance, oh, OK, thanks. So in the no instance, this is the matching. But in the yes instance, suppose that we also add the matching among the A vertices. So this increases the size of the matching by 3/2 times. So any better than 2/3 approximation has to distinguish these two cases. Okay. Now, OK, I want to argue that intuitively this this distribution requires ND time. It takes ND time to separate these two distributions. So also I wanted to point out that I'm going to randomize the vertex ID. So I'm not going to tell you which sets a vertex belongs to, unless it's an S vertex or a T vertex. I'm going to give them the list of vertices in S and T to you for free. The only thing that's hidden is if a vertex is in A or B, if the rest of the vertices are in A or B. And that's what's going to take a lot of time, hopefully. I mean, this is a running distribution, but yeah. So now suppose that we want to check if a vertex V, which we know is either in A or B, belongs to A or B. Suppose that we want to check this. So what's the natural idea? The natural approach is to take this vertex V and scan all of its neighbors until seeing an S neighbor. And if you do not see an S neighbor, it's going to be in A. If you see an S neighbor, it's going to be in B. OK. But how long does it take for this vertex to see this S neighbor? Every vertex has at least epsilon n neighbors in the dummy vertices T. So if you randomize the adjacency list in the input, it takes actually omega n time for every vertex to see this S neighbor, if any. So for any vertex, checking if it's in A or B requires n time. On the other hand, to separate these two distributions, we have to see if there's an AA edge in the graph or not. Okay? So what can we do? The naive algorithm is as follows. Take a vertex in A, for example, take a random vertex, check if it's in A in order n time. Repeat this a constant number of times until finding an A vertex. And then you check all of the neighbors of V until, and for all of these neighbors that are in the core graph, check if they are A or B. Okay? But if you want to do this for every one of those neighbors, there are D of them that are in the core. The D of them go to either B or A. And if you want to check the span n time, this is ND time, n to 1.2. Okay? So this is why this distribution might seem to require ND time. But unfortunately, there's actually a smarter order n time algorithm for this distribution. So I'm going to tell you what the algorithm is, because it also sort of shows that to prove lower bounds, we have to be careful about this kind of algorithms. So what is the algorithm? Suppose that I start with some vertex V in A. Again, this can be done in order n time. Now I run a 2D step random walk from V. Okay? A random walk only on the core. So if the moment I step into T, I just backtrack and continue in the core only. Okay? So how long does it take to go from V to the next neighbor in the core? there are d neighbors in the core. So basically, d out of the n neighbors are in the core. So the probability that if I pick a random vertex being in the core is roughly d over n. So it takes roughly n over d time to find the next neighbor of v in the random walk. Okay? And then I continue the random walk for 2d steps. When I'm in this vertex in B, I go back to A. In the node distribution, the intuition basically is that in the node distribution, every time I'm in A, I go back to B, and every time I'm in B, I go back to A. So after an even number of steps, if I start from A, I end up in A. However, if we are in the yes distribution, at every step that we are in A, there's a 1 over d probability that I actually go through the AA edge. So if I do this for 2d steps, there is a constant probability that I pass through an AA edge only once. And in this case, I start from an A vertex and end up with a B vertex and can separate the two. Because the total length of the random walk is d, and every step takes n over d time, this overall takes n time. Yeah, so the takeaway out of this algorithm is basically that these long query paths, here the length of this path is in the order n to the 0.2. These long query paths could actually be helpful in designing algorithms. I mean, I do not know an algorithm in general that uses these long paths. But at least when we are proving lower bounds, we have to be careful that we sort of like take these type of algorithms into account as well. Okay? So I'm just going to tell you how we get around this algorithm at least. So the idea is, suppose I just want to kill this random walk-based algorithm. So what I do is I also add some epsilon d edges, an epsilon d degree random graph between the B vertices. Okay? Now if you do the random walk, no matter if you're in the yes instance or in the no instance, whenever you are in a B vertex, there's a constant epsilon probability that you actually go to B again. So morally what happens is that if you run a random walk for these steps, the last vertex in the walk is actually pretty much independent. Its AB status is pretty much independent of the AB status of the first starting vertex. Yeah, so yeah, you have to be a little bit careful. You have to change the size of B for this graph to be realizable. But basically, this is pretty much the distribution. Yeah, and you may be wondering why we set d to be n to the 0.2 and not larger. If we are proving an nd lower bound, why not just set d to be n? And the reason is that in the analysis, we use how large d is. So basically, how much time do I have? 5 minutes. OK, good. So yeah, so I can actually give a rough overview of the analysis as well. Arguing why this d cannot be larger than n to the 0.2, at least for our proof. So the idea behind the analysis is as follows. So the first useful lemma that we prove is that if the algorithm makes less than n to the 1.2 queries, which is the lower one we want to prove, if the algorithm makes less than these many queries, then the induced subgraph of the edges discovered by the algorithm in the core actually form a forest. It's actually a directed forest, depending on the directions that those edges were discovered. Why is this? So actually, let me give a proof sketch of why it's a forest. And this will be a forest only if the degrees are n to the 0.2. If the degrees are larger, it's not going to be a forest anymore. Basically, every query that we make, the probability that it ends up being an edge in the core is roughly d over n. This is n to the minus 0.8. So overall, we discover a total of q, the number of queried edges, times n to the minus 0.8 edges in the core. A lot of other edges go to the dummy vertices, which are useless. So this is n to the 0.4. This is n to the 1.2 minus 0.8. This is n to the 0.4, basically. So this is the total number of edges in the core that we see. Now take any pair of these this is the total number of edges and also the total number of vertices. Now take any two of these vertices. So there are n to the point 8 of these pairs. And condition on what you've seen so far, condition any set of n to the point 8 vertices, n to the point 8 pairs. Now if the graph is random, the probability that there's an edge between them is, between any two of these vertices is d over n. So it's going to be n to the minus 0.8. So these actually cancel out, and with large enough probability, there's never an edge in the original given graph between the vertices that you've discovered. So this is a little bit hand-wavy because the graph that we construct is not actually a random graph, it's a regular graph. But if it's picked from the a random set of regular graphs, you can still manage to prove this. OK, so the first lemma is the algorithm only sees a forest. And now if the algorithm sees only a forest, the problem becomes much nicer to deal with. So for example, suppose that we start from this vertex. That's an A vertex. We do not know if it's an A vertex or a B vertex. So we start querying edges for this vertex. Maybe the next neighbor is a B vertex. We make these queries, and then at any point we can expand this tree. We can take any vertex, query another edge. And yeah, so we see some tree. And while we're exploring this tree, we have no idea if the vertices that we've seen are A or B until we see S vertices. Whenever we see an S vertex, the information that we're given is that its parent must be a B vertex. Okay? So basically what happens is the algorithm discovers a tree like this. The white vertices could be A or B. The gray vertices are S. We know which vertices are S. So the moment we see an S vertex, we know that we've seen an S vertex. But then we have to guess if we've gone through an AA edge or not. In condition on having seen this tree, different outcomes could be possible. For example, here, this is a possible outcome. Here, we have passed through an AA edge. On the right, we have not passed through an AA edge and have seen the same tree. Basically, the question is, how large does this tree have to be for it to be statistically significant enough for us to be able to distinguish the yes and no distributions? And yeah, so how much time do I have? 2 minutes. OK, awesome. Yeah, so ideally, we want to say that for any t that's small enough, the probability that it's drawn from the yes distribution is the same as the probability that it's drawn from the no distribution. If it's small, if we prove this, we're done. That means that the tree has to be large for us to be able to distinguish. Unfortunately, this is not possible to prove, because here's a very small tree that actually can separate the yes and no distributions. Here we have this vertex, and we've explored all of its neighbors, all of its d+1 neighbors in the core. None of them end up being an S vertex. That immediately tells us that this vertex is an A vertex, because a B vertex must have an S neighbor. And then suppose that the tree continues querying another neighbor of this vertex, and it also doesn't see any S vertex and has queried D neighbors. So this is a very small tree of size D that just gives us, that separates the two distributions. So the proof has to be a little bit more complicated. So what we show is inductively that even though there are small trees that can actually distinguish, they're very hard to find. In particular, we prove that for the likely trees, so I'm going to skip this slightly technical slide, and we prove that for the trees T that are likely for the algorithm to find, the probability that they're drawn from the yes distribution and the no distribution are the same, almost. And so it's hard to distinguish the two cases. And I just want to throw out a buzzword here. The proof relies on correlation decay, and I think it's really nice that correlation decay is playing a role. I have not seen many other sublinear time lower bounds using this. So basically, intuitively what it's saying is precisely the reason that we had to kill the random walk algorithm. The random walk algorithm queries a long path, and from that learns something very important. With correlation decay and the new distribution, we say that if you've queried this forest, the status of two verbs is far enough, further than log n, for example. Their A/B status are going to be almost completely independent from each other. Yeah, so correlation decay has played a lot of has played role in a lot of other results, mostly in the algorithmic side. But here, I think it's really nice that it can be used to prove lower bounds in the sublinear model. OK, so let me conclude. So there are a lot of exciting developments on the algorithmic side for sublinear matching. You can get a half approximation in n time. This is time optimal up to polylog factors. You can improve it a little bit, spend a little bit more time. You can improve the approximation significantly to 1 minus epsilon in subquadratic time. And I also want to point out that there's also this other 1 minus epsilon approximation by Yoshida, Yamamoto, and Ito running in delta to 1 over epsilon squared time. So this is, if the graph is low degree, this is pretty fast. On the lower bound side, we saw the Parnason run lower bound of omega n for any constant approximation. I also outlined our 2/3 plus epsilon approximation lower bound of n to the 1.2. And I also wanted to make an announcement here that so we recently were able to improve that this Yoshida, Yamamoto, and Ito result is almost optimal. We proved that for a 1 minus epsilon approximation, delta to 1 over roughly epsilon time is necessary. So delta should be smaller than n to epsilon. So this doesn't really imply anything for the dense regime. But still, for the sparse regime, the gap is now delta to 1 over epsilon squared versus delta to epsilon, which I think is perhaps a little bit surprising. And also, yeah, so that's what we know. I also want to mention a few open problems that are interesting to me. Generally, like better understanding this approximation running time trade-off is super interesting. For example, a very nice question is, what is the best approximation that you can get in n polylog n time? Currently, we know half. But the lower bounds actually rule out, with the lower bounds, it's still quite possible to obtain all the way up to 2/3 approximation in order n time. So maybe you can apply EDCS. Who knows? Another open problem that's interesting to me is it possible to obtain a 1 minus epsilon approximation in n to the 1.99 time? Think of epsilon as a very small constant, like 10 to minus 10. Is it still possible to get it in n to the 1.99? I want the exponent to be independent of epsilon. I think that would be super interesting. Ruling it out would also be super interesting. So generally proving better lower bounds, maybe there's a way to handle cases where the queried graph is not a tree. That would be super interesting. Yeah, and with that, I'm going to conclude the talk. Would be happy to answer any questions.
Wondering about sublinear time actual computation of a matching, but of course in some implicit model like the Rubinstein model, local computation or something like that. So you implicitly compute the structure, and for any match you can consistently ask if it's in the data structure or not. Is anything more?
Yeah, that's a great question. Yeah, so the lower bound that I mentioned, the n squared lower bound for finding any matching, that's if you want to just outright write down what the matching is. Another way to look at it would be I query this vertex, and you have to give me an edge of this vertex in the matching if it is matched. This is almost what we are doing in this model in estimating the size. The only exception is that the starting vertex is a random vertex, not any vertex. But there are also a lot of works on just answering these kind of queries for any vertex, designing those oracles when any kind of vertex in the graph is queried. Yeah, the LCA model is exactly the right thing to look at. Yeah, so this, for example, delta to 1 over epsilon squared algorithm of Yoshida et al. Works in the LCA model. The lower bound of delta to 1 over epsilon also works in the LCA model. So yeah, it's a super interesting model as well.
It's kind of a big question, but so in sublinear algorithms, you can kind of either focus on the number of queries or focus on the harder thing of running time. So I guess for the algorithms you showed, they're the same, but is that generally like kind of usually free, like usually the low query algorithms also get the running time, or is there a lot of extra?
For matching, I do not recall an algorithm that has running time much larger than the query complexity. So almost all of these results, I think, have the same running time up to polylog factors as the query complexity. For other problems, of course, you can, for example, yeah, minimum vertex covering general graphs. Yeah, there could be separations. For matchings, I'm not aware of an algorithm that uses more time than the query edges, or yeah, unless someone else knows that wants to correct me. Yeah. Great question.
I think it's a question related to what Aaron asked earlier. You know, in all of these are local query models, but there are also global queries that I can ask a cut query, for instance, in the entire graph. And it might be that those may have application to dynamic graphs also, because you can implement the query or object. And there, I don't know anything about matching, but some problems have polylog and time algorithms. Do you know anything for matching there?
That's a great question. Yeah, I do not know much about settings other than adjacency lists and adjacency matrix for matchings. Yeah, that would be super interesting, especially if they can be implemented in the dynamic setting. Yeah, because the problem is that these lower bounds that we prove for sublinear matching do not imply dynamic lower bounds, because there could be other ways to use other sublinear algorithms. Yeah. Great question.
What's your lower bound model here? Adjacency list or matrix?
Yeah, they're adjacency lists. We believe they also work in the adjacency, the 2/3. We believe it also works in the adjacency matrix model. We just have not written it.
If instead, if we consider MIS problem, could we hope to get anything better than n squared?
You want to estimate the size of MIS? Yeah, that's an interesting question. I have not thought about it.
Lower bands all seem to assume that the adjacency lists are shuffled.
Yeah.
It seems like a crucial step. In some settings, you could assume that the adjacency lists are in some order from a vertices perspective. Is there anything for that setting?
That's an interesting question. So yeah, the question is, here we assume significantly that the adjacency lists are randomly shuffled in the distribution. In particular, we use it in the part where we said that majority of the queried edges actually go to the dummy vertices. So if we could somehow exclude the dummy vertices fast, or if the dummy vertices, the edges to the dummy vertices were the first vertices in the list, then these lower bounds break. Yeah, I think it would be very interesting to come up with another, I don't know, maybe like, yeah, again, going back to the dynamic applications, if it's possible to come up with a certain way of sorting these lists that allows for faster algorithms of breaking these lower bounds, I think that would be super interesting.
I have my own question.
Yeah.
So in the same paper for data and two-third approximation, you had n to the 1.99 area.
Yeah.
So it shows you cannot push this n to the 1.2 minus 1 complete the point all the way to the
Yes. Yeah.
So how far do you think you can push this? Can you push this to, do you think you can push this n to the 1.5 minus 2?
Yeah, I do not necessarily think that n to the 1.2 is the right answer here. I think the barrier is the queried edges forming a forest. So it's sort of like a barrier in the analysis, not necessarily for the problem itself. I think it would be very interesting to see how far we can push the lower bound. Yeah, as you said, you cannot push it all the way to n squared. The result in our paper implied that. Also, this newer 1 minus epsilon approximation in subquadratic time also implies that. If you can get 1 minus epsilon approximation in subquadratic time, of course, you cannot prove a lower bound that better than 2/3 approximation requires n squared. Yeah, very good point.
Let's take all the questions offline. We will be done taking certain